It's my great pleasure to introduce Alberto Rodriguez as our speaker. Alberto is a wonderful colleague, and I think he's a roboticist who really is anchored in mechanical engineering and thinking about the kind of mechanics and sensing and control aspects of manipulation. Alberto came to us, he did his PhD at Carnegie Mellon, working for the very famous Matt Mason with an impactful PhD that won 2 Best Student Paper Awards. Alberto, before that, was at UPC in Barcelona and for his undergraduate study, and he has amazing taste in problems. He's won 6 Best Paper Awards with another 6 Best Paper finalists, if I've counted correctly, as well as a clutch of other awards such as Amazon Picking Challenge, various first, second, third places, and IEEE Robotics Early Career Award. Alberto has a wonderful cohort of students. I love to pass his lab and see the kind of excitement and energy all hours of the day and night. And he's also very active on campus as a housemaster at SIDPAC. And he's been a dedicated teacher, especially in 2003, where he's taught, I think, at about 11 times, with about 6 times as instructor in charge and 3 as co-instructor in charge. And so Alberto's contributions run the whole spectrum of making MIT a better place and making an impact on the world through advanced robotics manipulation. So it's my great pleasure to introduce him to speak to us today.
Well, thank you, John, and thank you, Matthias, for all the organization for making this happen. I guess I'm going to share my slides. Is that the idea?
Yes, that would be a good idea.
Okay. So here. All right. Thank you, everyone, for joining. And I hope that you are as excited as I am about the end of the semester, how close we are. And I hope that you all have some time to recover energy through this well-deserved break that is just around the corner. So today I wanted to have a chance to talk a little bit about manipulation. I will show some of the latest work that we've been doing in my group in the MCube lab. And before that, I will also spend a little bit of time talking about sort of manipulation in general, my perspective on where we are as a community and some directions that I think that are important to explore. In particular, I will talk about manipulation primitives and the role that I think that they ought to play in building dexterous robotic systems. Okay, so robotic manipulation, if we look at classical industrial applications, robotic manipulation that has for the most part been exploited or understood as the idea of like picking up objects one by one and putting them from here to there in a very precise way and with very with high efficiency, but still moving objects one by one. So here are some examples in the context of lab automation, automobile automation, and warehouse automation, where in all of them, the idea is that these robots are doing almost exactly the same thing all the time. And this perspective has been extremely successful, right? So we can see here an example, sort of the continuous rise of the number of robotic arms that have been sold in the last decade or more, and it's like a healthy curve. And while it has been extremely impactful, I think that the idea that we have in our head when you think about manipulation is quite different from the way that sort of these robotic systems are developed or are implemented. And one key question is why that's the case? What leads to this particular approach not generating sort of the smooth, flexible, and sort of graceful many times behavior that we see when we, for example, use our hands, right? So when I think about manipulation, I think of the example that I want to show is sort of my daughter's crafting table, right? So for me, manipulation is everything that happens in this table, right? So it's has to do with using tools. It has to do definitely also with moving objects around. But moving objects around maybe is probably one of the most boring things that happens in this table. And it has to do with exerting forces, and it has to do with sort of stacking objects, sort of some of the classical problems that come to mind when we think about robotic manipulation in research. But it's much more than that, right? So to me, it's here where sort of the cognitive and the physical are sort of interacting at their best. In a scenario like this, it's rarely the case where we see two instances that are exactly the same, where you can execute the same behavior, right? So there's a gigantic amount of flexibility in the way that we're interacting with objects here. And not just there's flexibility, but it is something that is rewarded, right? That we seek. The creativity that comes with using our hands in sort of in creative ways to sort of bend the world to our will. To me, that is what is manipulation. And in many respects, we're very, very, very far from being able to understand how that process is sort of replicated in machines. To some degree, because manipulation is as much engineering as it is an art, right? So it's something that we do with a completely unconscious understanding of how we do it. So it's very difficult to reach to a holistic understanding of that process. Anyway, so today I wanted to talk about sort of different perspectives that the robotic manipulation community has taken to approach robotic manipulation. I will talk in particular about robotic manipulation, not robotics in general. And these are not all perspectives that that the community has embraced, but I think that these are four perspectives that I think are quite important, or that represent a significant amount of research in our community. And then I also want to talk about the role that manipulation primitives play in sort of integrating these different perspectives. And then I will describe that in the context of two recent research lines that we've been developing in the MQ lab. Okay, so let me move forward. This is an example that I've used many times. And in fact, I used this example when I gave a talk in the MechE colloquium 2 years ago. And the idea is this is myself sort of reaching into a shelf and picking up a book from the shelf. And the idea is to sort of try to rationalize or understand what's happening in that process. How come that I can do something like this in a completely sort of effortless way without having to think about it, but at the same time with so much grace, not just me, but just anyone. And while when you sort of try to analyze this problem, there's very large complexity in sort of try to replicate something like this. So today I wanted to use the same example to illustrate these four perspectives. So for example, one perspective that the community has embraced is to think about it from a mechanical perspective, right? So from a mechanics control perspective. So we make simplifying assumptions about the geometries and about the laws of mechanics that explain the interaction between the end effector, in this case, my palm, and the book. Maybe I can think of my palm as 4 points or a plane, and the book also as a plane, and it's sort of the interaction between these two planes and the maybe Coulomb friction law that I use as a reduced model to then be able to control in a feed-forward fashion the interaction, right? How do I generate trajectories that bring my simplified representation of the mechanics through the underactuated control that I get from having to exert forces through contact? So that's a significant perspective that has been embraced by the community at large for many decades. But you can also think about this problem of the interaction between the palm and the book from a haptics perspective, right? So someone might say, well, actually what matters really here is forget about the model of the mechanics. I mean, unless I have the ability to exert forces, right? So if my mechanics tell me, yes, you should contact here and exert this force, I don't have the ability to exert that force unless I care about the haptic interaction, right? How do I render forces through this very complex interaction between a soft object, which is my hand, or semi-soft, and a rigid object that is the book. A significant part of the community has also think about manipulation from that perspective. How do you render forces in a highly complex or unmodeled environment? Now, we can also think about this problem from a planning perspective, right? Someone can say, actually, what really matters here, where the complexity is in generating a trajectory, a sequence of actions that bring the book from between those clearly different strata where it's going through, right? So first, the book is sliding on the wall, and then it's sort of pivoting maybe about the edge of the shelf, and then finally it's in the crust. How do I chain a sequence of long horizon decisions that bring the book through that trajectory? And then someone else might say, actually, what really matters about this is that the book is a physical object that lives in the real world, and I don't have a model for it. It's just the perceptual, the visual perception that I get through my eyes. And what tells me that the side of the book is a good place where to put the palm, or that the edge of the book is a good place where to put my thumb, right? And definitely that has also been a perspective that has been embraced lately with higher emphasis in the robotics manipulation community. Now, you might be thinking, I'm really not saying much new here, right? So these four perspectives are classical in robotics, and we can think of them as, we can structure them, for example, by the nature of the decision process, right? So here we're just saying that, well, maybe we're just thinking about it from a feed-forward perspective, right? So I have a model that I can simulate forward, and that is what allows me to make decisions about how to generate behavior. What I can think about it more from a feedback perspective, right? So it's in the sensor space where I make my decisions, that where the information lives that allows me to make those decisions. Or I can think of this structure from a local versus global perspective, right? So I might be caring more about the fine-grained interaction between the end-effector and the book, or I might care more about the global state of the task that I'm executing. So there's clear structure for associated with these perspectives. I might also sort of structure them from the nature of the challenge that they address, right? So each one of these perspectives acknowledges that there's or gets excited by certain challenging aspect of interaction, right? So you might get excited by the anti-actuated and hybrid frictional dynamics that are involved in transmitting forces through contact. Or you might get more excited by the generality that comes from creating long horizon behavior. So you more naturally would tend to think about sort of a search planning perspective. Or you might get more excited by the challenges involved in generating real forces, in rendering real forces and velocities at contact, right? Or from the challenges involved in having to manipulate real worlds, where the perception comes from vision. Or finally, we can also structure these perspectives from our also time perspective, right? So from the nature of the dynamics of research, of how sort of our ideas or ideas in the community evolve over time. We can think of maybe robotic manipulation sort of originating, and actually a lot of the work in this department, right? So in the area of haptic feedback, right? So with everything that has to do with impedance control, everything that has to do with force control, right? So great excitement about how do we understand interaction from a feedback perspective. And over time, some of that excitement sort of gradually moving, and this is just sort of broad strokes of the dynamics, right? So all of these perspectives coexist at the same time. But I think that there's been some sort of dynamics that have moved through this cycle of perspectives, like gradually going to a more mechanical perspective, where suddenly we care more about things that have to do with peg insertion, with fixture design or grasp analysis, right? Where we care more about the mechanics of manipulation. And over time, more of the community gravitating towards configuration space approaches, where we care more about the long-term searchability of trajectories. And maybe more recently, in the last decade, much more emphasis on the visual perspective of manipulation, right? So some of these dynamics or some of these motions clearly influenced by the technologies or the hardware or the techniques available at the time, right? So these days we're excited about neural networks that have sort of a natural ability to process visual data. So that has generated excitement in that sort of lower right corner of the perspectives. But I want to think that there's also, I like to think about research dynamics as also sort of a pair of pendulums with very slow natural frequency, where sort of these interests sort of go back and forth. And I think that I can sense that the community is also gravitating now towards going back into a more control perspective for controlling haptic interactions, with the rise of sort of tactile feedback, with the development of robots that can generate forces now, that can implement more easily impedance control. I can sense sort of that the community is gravitating again in this cycle. So, which is great, but at the same time, we have to remember, and this is sort of where I wanted to go, that ultimately we have to prevent going in cycles in these sort of research in these research directions. And ultimately, the problem that we want to solve is at the center, right? So we need to find ways to integrate these perspectives. Building general manipulation systems requires thinking about all of these at the same time, for performance, but also for simplicity. And this is where manipulation primitives come in place, because by focusing the analysis on specific interactions, they allow us to find synergies between these perspectives and exploit them. Okay, so all of these, just to sort of put an idea or an image of different ways that we can think of interaction, that we can think of generating autonomous behavior through contact, leading to the description of what is the role that I think that manipulation primitives play in solving this challenge. So what's a manipulation primitive? We can think of different modes of interaction, right? So from the left side of the image of the slide, you can see grasping with the fingers, or pushing an object, or pivoting an object, or pulling an object. The idea is that you prescribe some specific type of interaction that comes with some expectations in terms of the contact dynamics, or in terms of what is the motion that we want to transmit to a particular object living in the environment. And by focusing on one particular type of interaction, that has sort of naturally allowed these different perspectives to sort of evolve and find sort of implementable solutions. But I want to argue that they also facilitate integration. And that's what I will go into with the two examples that I show of current research in my group. Okay, so if we look at just one example of primitive, let's say pulling an object. What is a primitive, right? So it's as an assumption on the contact interaction. In this case, it's a palm that is contacting an object on the top of the object. And the assumption here that we're making is that the palm is going to be sticking to the object. And that sticking interaction comes with benefits in terms of simplified mechanics and sort of simplified forward model for the object motion. So if I'm making the assumption that there's this rigid sticking interaction between the palm and the object, then that reduces the complexity, right? So I can think of the mechanics of the interaction between these two as some form of quasi-static equilibrium. It is the friction between the object and the palm and the object and the ground that determine that will eventually determine the motion of the object. But if the object is sticking to the palm, the force resolution is simplified. And from a controls perspective, I can then assume that the motion of the object is a fully actuated kinematic trajectory. I don't need to reason about the hybridness or under actuation involved in transmitting forces through contact, because I'm precisely making that assumption that the object is going to stick to the palm, and also allows to sort of get some simple models on the reachability of what is it that I can achieve with this primitive. For example, if this primitive is pulling the object with the palm on top, I know that the object will not be able to sort of pivot or change facets. So I can only move this object on this table in this case. So on one hand, reduces complexity of the mechanics models we have to use to compute for the forward simulation, or the mechanics models we have to use to plan trajectories. And on the other hand, it sort of clarifies the division of roles, right? So if this primitive is making an assumption on the type of contact interaction, which is maybe a rigid sticking interaction in this case between the palm and the object, then I can directly say that the role of haptics in this case is to monitor and enforce that sticking interaction, right? So I need to develop a controller, a haptic controller, that will take care of making sure that this assumption is satisfied. And then the role of vision would be to find places where to interact with this object that will make it possible for the haptic controller to do its job. In this case, that it will render sufficient information to be able to know whether it's sticking or not. So on one hand, it can reduce complexity, and on the other hand, it sort of clarifies this division of roles. So I want to get deeper into this relationship between defining primitive interactions between an end-effector and an object that we're manipulating, and finding integrations between these different perspectives. So first I will describe, and let me look at the time. Okay, I think we're good. First, I will describe recent work that we've done in trying to integrate haptic feedback with mechanics and control. The idea of integrating tactile feedback in dexterous manipulation. So how do we generate dexterous behavior that can consume tactile feedback in real time, and to generate reactive behavior? And the second research line that I will describe combines the bottom two rows in the bottom row of the four perspectives, and it will try to generate dexterous behavior by using visual cues or visual affordances. Okay, So dexterity with tactile feedback. The idea is that we want to embed tactile feedback in the mechanics, in the models of mechanics that we use for generating dexterous manipulation. And we start from the definition or the idea of what the manipulation primitive is, which is a certain assumption on contact interaction and some expectation on the motion of the object. And this naturally sort of partitions the role of tactile controller, the controller that is tasked with generating robot behavior, into two different controllers. The first one is in charge of controlling the contact state between the end effector and the robot. So the idea of imposing this assumption that the manipulation primitive is defining. So this would be a controller whose role or whose task will be to make sure that the contacts that we're assuming that they're sticking, they are sticking, or that the contacts that we're assuming that are slipping, that they are slipping, or if we're assuming that something is in a stable cross, that it will continue to be in a stable cross. And the role of the second controller will be to control the state of the object or the motion of the object. And it will do it through exploiting the assumption that the manipulation primitive is making. That assumption, as we were saying before, creates some simplicity in the mechanics or in the controls problem. And by exploiting the assumption, we can sort of generate behavior for controlling the object. Okay, so the first system that I wanna sort of illustrate this framework, in which I want to illustrate this framework, is a dual arm system with two palms that have two tactile sensors integrated. These are tactile sensors that are based on gel side technology. The basic idea is there's a camera inside the palm that is looking at the deformation of the skin of the palm. And by looking at the deformation, we can see either the geometry at contact, or we can see also we can estimate the contact forces at the interaction. Here's an example showing how, in this case, we're just moving the object. And on the left, you can see how we can estimate, in this case, as a simplified scenario, just a line is an edge of the object. And on the right-hand side, we can estimate sort of the stress or the shear forces on the skin of the sensor. And with that, understand whether it is slipping or it is not. So we can think of this problem. The question is, if the goal is to bring the object to a particular configuration, in this case, the blue box, we want to bring it to the shaded blue box, how do we generate motion for the robot arm? And while there's sort of, this is a hierarchical problem where we need to think about generating arm trajectories that move the palm, and then palm trajectories that move the object. Now I'm going to focus just on the interaction between the palm and the object. And the idea is that this is sort of the same primitive that we described before, just pulling the object. And we're going to live by the assumption also that the palm is going to stick to the object. So the contact state controller on the right will be in charge of tracking whether the object is sticking or sliding on the palm. And then depending on whether it's about to slip or not, then control the normal force or control the force that is applying to the object. And then on the left-hand side, the role of the object state controller will be to generate trajectories that bring the object to the shaded blue box, based on its current estimate of where the object is, and based on the assumption that the object is going to stick to the palm. And because it's making that assumption, it can do faster planning. So on the left-hand side, just the object state controller, we see that the moment that we're perturbing the object, sort of the arm is replanning to try to bring its current best estimate of where the box is to the shaded blue box. And then on the right-hand side, the palm is sort of estimating in real time whether the object is slipping or not. And if it's slipping, it's sort of applying higher force. And it is this contact state controller that is interesting from a primitive perspective, because we can think of it in generality. We can think of what it takes to enforce a certain kind of contact configuration. Imagine here that we have a primitive that is making a certain assumption about the multi-contact configuration between the object, the environment, and a certain number of fingers. In this case, there's 2 contacts between 2 palms, and there's 1 contact with the environment. And the goal of this controller, in the case of this primitive, would be to try to maximize the stability of this contact configuration and prevent any of the contacts from slipping. So we derive a model of the stability of this particular contact configuration. Each contact has its own friction cone, represented in the diagram here by the dotted lines, which basically means that if the contact force is inside that cone, the contact will stick. The moment that the contact force, which is the blue arrow, goes outside the friction cone, it will slide. It will not have enough friction to maintain that contact. So the idea is we will want to maximize the minimum distance, or we will want to make sure that these blue arrows or the contact forces will be as far as possible from the edges of the friction cone at all time. So we formulate this as an optimization problem where we maximize some margin of stability. This phi here, phi I, is the distance, the angular distance between each one of the contact forces and the edges of the friction cone. And these betas are just some scalars that are sort of weighting which one of the contacts we care more, depending on the context of the execution of the primitive. And the decision variables in this optimization problem, in this case, is delta Q, which is sort of the adjustments that the end effectors have to do. In the case of this example here would be the reorientation of the palms, which how much do we want to rotate each one of these palms to maximize the stability of the grasp, and the W's, which are the contact wrenches of the active contacts. In this case, it would be the 2 contacts, contact forces at each one of the palms. We can control how much we're squeezing on the object. So those are the decision variables, and we want to find which update we have to do to those decision variables subject to certain constraints. And the constraints are classical within manipulation, right? So we want to make sure that we satisfy force equilibrium, that the contacts can sustain the external wrenches, like gravity, for example, or other known external perturbations. And at the same time, we want to impose Coulomb friction cone constraints that contact forces can only push, and they have to live inside the friction cone so that it sticks. Okay, so if we were to be able to solve this optimization problem in real time, we could generate a behavior that feeding from the tactile information. In this case, it would tell us which one of the contacts is in higher danger of going to the other side of the edge of the friction cone, and we could up its weight in this optimization problem, and then resolve these in real time. Unfortunately, this optimization problem it's difficult to solve it in real time because the margin, the way that is defined here, is a trigonometric function, so it's not convex, and the equilibrium constraint is bilinear because we are changing both the W's right here, the contact forces, as well as the Jacobians of the contacts, right? So the changing the orientation, in this case of the palms, changes these Jacobians, and this is a bilinear constraint. So what we do to be able to consume tactile information in real time is to approximate the margin by a convex, or using a convex approximation, which is classical from, for example, the locomotion community. I'll show in a second. And then we linearize the equilibrium bilinear constraint around the current configuration. So we substitute by this problem, and we substitute the exact margin, which would be this angular distance, by this distance, which happens to be convex now, this alpha. And then by doing these approximations, we can solve this problem in real time sufficiently fast, so that then we can generate this type of regulation behavior, right? So here we've told the robot that it has to maintain the object in that center position. And by combining these two controllers, one that is sort of controlling the downward force and another one that is controlling the trajectory of the object, is sort of creating this reactive regulation behavior, which then we can put in the context of a trajectory planner that is capable of sequencing primitives, and then we can tell the robot to bring an object from one configuration to another configuration in a reactive fashion. And again, one of the key enablers that allowed us to do this fast enough to be able to consume tactile feedback is that we decompose interaction, or we restricted interaction to only those to only some primitive modes of manipulation interactions that on one hand had simple controllers, so that we could run them fast enough to recompute object trajectories, and that generated tactile feedback that was informative enough to understand sort of if the contacts were slipping or not slipping in real time. So using primitives was essential in this case to make the connection between these two perspectives. One limitation of this work is that this is only looking, if you remember, at the forward perspective, at the two quadrants that are at the top row. So this is a very local perspective, right? So the robot doesn't know much about the object itself, right? So, well, on the contrary, it only works because it has sort of a model of the object, but it doesn't know where the object is. We have to tell the robot more or less where the object is, and then specify a particular reconfiguration, desired reconfiguration. It doesn't use vision integrated into the loop. And it needs to know a geometric model of the object so that it can interpret the tactile cues in the context of the actual geometry of the object. And in the second application that I will show soon, we will solve the opposite problem, which will be using visual feedback instead of tactile feedback. But before that, I just wanted to show quickly another example of a system where we've also implemented this sort of the composition of tactile dexterity into two controllers, one controlling the contact interaction and the other one controlling the object state. just to illustrate that it's not just restricted to imposing sticking configurations, but it can also be used for allowing objects to, or fingers to slide on objects. This is a very different task. The idea is that we want to manipulate cables and we want to do it in a efficient manner. And this robot is tasked with grabbing a cable and then sliding its fingers along the cable. And classical approaches to tackle this problem have been heavily biased or focused on a visual perspective, on a visual pipeline, where the idea is that you have a vision processing pipeline that is capable of estimating the full state of the rope or of a cable, and then planned motions for the arm to be able to manipulate the cable based on that state. But in reality, that is not necessary, right? So the interaction between the gripper and the cable is very local in this case. So we set out to demonstrate that it was possible to do that task just with tactile feedback. And the key to be able to do it is to run two controllers that, like in the previous case, sort of work in combination to make the task simple enough that it's possible to do it with a simple model of the mechanics of this task. So let's see how this works. The idea is that we have, again, an object state controller tasked with just controlling the state of the cable in the fingers. And in this case, by state of the cable, we mean the exact location of the cable. So whether it is at which angle and in what configuration inside the fingers. And then we have a contact state controller that is monitoring the forces, the frictional forces, when we're sliding the cable. So you can see some rough pulse estimation of the cable in the fingers and some rough estimation of the frictional forces when the cable is sliding. So unlike in the previous example where we wanted the end effector or the fingers or the palms in that case to stick to the object, in this case, we want the fingers to be able to slide on the object on this cable. So we will have a contact state controller that it will control the gripping force fast enough to be able to regulate the frictional force when the cable is sliding to a particular desired value, right? We don't want the friction force to be very high because the cable will get caught in the fingers. And we don't want it to be very low because on one hand, the cable can fall. And on the other hand, if you don't grip hard enough, you will not get feedback to be able to control the system. So we have a simple model of the cable finger interaction dynamics. On the left-hand side, we have this fixed gripper that is grabbing the cable. And on the right-hand side, this is the finger that is it's going to be pulling from the cable. And we model this as an underactuated system, a pulling system where if the cable is in this configuration, we want it to go back to the center and to be horizontal. And it is impossible because it's underactuated and we cannot make it go down directly, but we can work through the underactuation by planning a sequence of interactions or pulling motions so that it can eventually go down as if almost as if you're doing parallel parking with the cable. So we learn a linear model of the dynamics, the interaction between the finger and the cable, and then we just use an LQR controller to control it, which might seem like it might be too simple to model the complex interaction between these two objects that are sort of deformable and might have high friction. But the trick here is that the contact state controller acts as a regulator to make sure that the interaction is within a certain working point of friction, right? So we have this contact state controller that if we run it fast enough, it just wants to make sure that the amount of friction as the cable is sliding is within a certain threshold level. It's not too small and it's not too high. And by doing that, then the interaction dynamics between the cable and the fingers are sort of simplified in its range of possible behaviors. And by combining these two controllers, then we can sort of control the system. Okay, so the same idea as before. Now we use a different controller, right? Because it's a different primitive, it's a sliding primitive. While before we were looking at other types of primitives, but from a controls perspective, the composition into contact state control and object state control is the same one. All right, and last, I wanted to show briefly another piece of recent work that we've been pushing forward in the last year or so. This is work in collaboration with Pulkit Agrawal and Josh Tenenbaum. And the idea is now has been to combine sort of planning with visual cues or visual affordance space or visual cue space. We see an object for which we don't have a model, and we still want to manipulate it. And we want to sort of do a sequence of operations on that object to reconfigure it. And I'm not sure I'm going to have time to show everything, to do a full explanation of this project, but at least I want to show the motivation or the idea of why we're doing this project. So this is a video from the Amazon Robotics Challenge, the last year that we competed. And the idea is that this robot is tasked with picking up all the objects on one bin and bring them to the other bin. And it's manipulated objects that it has not seen before, and is doing it with a sort of speed and with high clutter in a high clutter environment. Again, it's using the idea of using different manipulation primitives for which it has learned perceptual models to understand which objects in the scene are graspable or which objects in the scene are suctionable. But without having to estimate the pose of the objects or the exact geometry of the objects. So this is what we call working in sort of in perceptual space. There are sort of cues that come out of the local geometry or the appearance of these objects that trigger the certain behaviors, or there's affordances in the perceptual space for certain primitives. So we get an image in the form of an RGBD, RGB image plus depth. And then we've learned affordance models with convolutional neural networks to estimate or to predict which of these locations in space are good locations to be able to suction objects or to grasp objects in particular orientations. And after looking at this heat map that represents the affordance in perceptual space is the point with highest score. That means that is the point that is most likely to be graspable in this case. So we pick up that point, and then the robot, it has never picked up that object, but nevertheless, it sort of picks it up in a correct orientation and by the handle. Why? Not because it has any notion of objectedness, but simply because the local geometry in that part of the space corresponds with what it has seen before, it has learned before to associate with successful grasps. So that's what we call sort of an affordance of that particular grasp. And this is a perspective or an approach that has been embraced significantly in the last decade, I would say, because the uprise of convolutional neural networks has made it possible to learn complex affordance models from lots and lots of data that have shown that have outperformed many systems that do some form of explicit state estimation, that first try to estimate the global geometry of the object and its pose, and then based on that, generate a plan for grasping it. So this is sort of something that has been embraced by the community and lives in the fourth quadrant at the bottom right that I described in the 4 perspectives. But there's one clear caveat, which is that by planning or executing motions directly in perceptual space, we've limited ourselves to be able to do sequential planning, like what we had, the perspective that we had on the bottom left corner of the 4 perspectives. We don't have the ability to sort of simulate how the system or what the state will be after we execute one action. So it is difficult to then decide which 2 actions to do in sequence if we wanted to do sort of a few actions in sequence. And in the last couple of years, we've looked at different ways to explore synergies that are of different primitives that are executed in sequence, like pushing and grasping objects, where we show that a system is sort of capable of learning when to push and then to sort of separate objects so that then it can grasp them, or how to grasp objects so that then it can toss them into particular boxes, and exploiting the synergies between these primitives. But in both cases, these 2 systems are explicitly avoiding doing any form of forward simulation of state, right? So when this system over here was pushing this block to the right, it did not have an idea of how the image or how the state will be after pushing it. It just had learned that in the long-term fashion, that was something that would be useful to do, and that in average, it would lead to the objects end up in a more graspable configuration. But it doesn't have the ability to simulate forward the state, how the image will look like after executing it. So that has clear limitations, right? That the community has been trying to exploit or sort of to explore. So there's been a lot of work in the last few years on visual foresight and trying to learn models that predict how what the camera will predict, what the image or video will look like after executing a certain action. Because if you want to solve a problem like this, where you have this red box here and you want to bring it to this configuration with some kind of motion like this, where you first do a pull and then you have to do a regrasp to bring it to a different sort of manifold of states, and then bring it all the way to the other side of the table, you need to do some formal prediction of how the state will look like to be able to generate this sequence of primitive interactions, right? So planning, long horizon planning requires some form of forward model that you can use to predict what the state will look like after each one of these interactions. And one key question that we've been quite interested is, how do we do this that when still the behavior that is generating each one of these primitive interactions is generated or is triggered still with affordance models that can generalize to more complex objects. Matthias, how are we doing on time?
We're going up against 5 o'clock, which would be the official end of the seminar, but it's so cool that we probably can go a little longer and ask questions afterwards.
Okay, so I'm gonna try to wrap up this part, but I think that I'll be done in 2 minutes or so.
Cool, and then we'll do a couple of questions.
Excellent. So very interested in the idea of how do we do planning with affordance models. So for that, we need to extend this notion of affordance so that it doesn't just sort of make a prediction of what is a good action to execute or a good primitive to execute for whatever is the representation of the state, the visual state. But on one hand, we need a more precise notion of affordance, something that tells us more precisely where to contact the scene and in which orientation. So if we want to manipulate with a palm, where to put exactly the palm and in which orientation, as well as a predictive model, something that allows us to fast forward time to see what the state will be like, so that we can change subgoals. And the idea is that, I'm gonna skip this, we need affordances to be able to predict contacts and to predict subgoals. And we can do that by learning explicit models of this new sort of generalized version of what an affordance is, where we give it a representation of the state or a representation of the object that we want to manipulate. And it makes predictions both of where to put the palm, so the contacts, and where to bring the object, so a subgoal. And we can do that because we're representing a state now as a point cloud, and because we're using primitives that are restricting to sticking interaction. And it's the combination of these two things that makes it possible to do simple forward propagation. It's just cropping a part of the point cloud and manipulating it as if it was that particular primitive manipulating that part of the point cloud instead of a model of an object. And it still captures sufficient part of the geometry of the world that we can sort of hypothesize where to put the palms or where to put the end effectors. So we learned that with a variational autoencoder, and we generate data in simulation by sort of manipulating many different objects, all of them cuboids in this case. But because we're learning these with affordance models, it sort of naturally generates a certain generality to a slightly bigger set of objects that are not just cuboids, as we show in a second. And then we use this model to sort of directly generate samples and subgoals, which then we integrate. This is sort of a more detailed description of what it means to do this in point cloud space with a graph attention network. And we do this sort of, then we integrate it in a sampling-based planner. So this is sort of a book, and the robot is tasked with putting it into a shelf. But the robot doesn't see a book. What it sees is sort of just a point cloud, which we render in simulation. And it still is sort of, it's capable of choosing the right grasp to pick up the book, to put it back into the shelf within sort of the kinematic reachability constraints of the platform we're using. It's compatible with long planning sequences, right? In this case, we've told the robot that it has to pull the object to the right and then grasp it to reorient it, and then bring it to the shelf and then put it here. But we haven't told it exactly how to do it, or where to contact the object, or how much to, where are the subgoals inside this long chain. And it uses the affordance model of the primitives that it has learned in simulation to be able to come up with a plan like this. And again, the key idea is that, or the key contribution is that it doesn't know the model of the object. It's just manipulating a part of the point cloud that it's seeing. And because of that, it has some degree of generality to objects that are not cuboids. So in this case, it's just planning the same thing, but with this object that in the point cloud space looks like this mustard bottle. And sort of it has an easier job in directly translating to real objects, because now the point cloud is coming from a real camera, but the point cloud representation looks quite similar to the simulated one. Here's just one example that I showed earlier with a two-step plan.
Alberto?
Yep.
There are a few interesting questions.
All right.
I don't know what your time plan is. Oh, perfect.
Yes, summary. Just wanted to highlight Francois Hogan, who is the main author of the first piece of work, and Anthony Simeonov, who is the main author of the second work that I presented. But more in general, and sort of very close to my heart, I want to thank everyone in the MCube family, without which it would be impossible to do anything of the things that I've shown today, right? So at the end, it is sort of a lab and a family that can push forward a research agenda like the one that we're pushing forward. So thank you very much.
Alberto, thank you. Fantastic talk. It's pretty amazing. There's a couple of questions out here. I want to first say thank you to all the audience for joining us today and seeing this amazing work. And we'll continue the seminar for a little bit to answer all the questions and to give Alberto a chance to actually respond to all the exciting things that you have been asking now. And I think the first one who was on here was Menglong Gu. So if I give Menglong the microphone, then you can ask a question in person. If you don't like that, let me know. I can ask a question as well.
Yeah, can you guys hear me? Thank you, Professor. It was a great talk. I was just a bit confused. What's the input to the system? Like, how much freedom do you get it to let it plan stuff? Like, do you just tell it to get this bottle or this point cloud to the final pose, or how does it work?
Mm-hmm. So in this case, the input is just the point cloud, right? So there's an RGBD camera that it sees a point cloud, and it is that point cloud is segmented. So we've told the system that whatever is on top of the table, that is the object that it has to manipulate. So it's you can think of it as a segmented point cloud. And the specification of the goal, what to do is a transformation a relative transformation of that point cloud. So we're telling it whatever that point cloud, that segment of the point cloud is, you have to transform it by this particular transformation in SE3.
Okay, awesome. Thank you.
Cool.
Okay. The second question is by Sreya Vangara, and I'm going to try to find our colleague here. Fantastic. Sreya,
Hi, Professor. I was wondering what kinds of classes would you recommend for students who are interested in this kind of work, both theory and project classes? And you don't have to recommend 2003.
Yeah, you should start with 2003 and then go to 2004 and then go up from there. No, that's a fantastic question, right? So I highlighted specific things of these systems that have maybe a more natural fit in particular courses. And for example, I would highlight Rustedrick's courses, right? So he has a course on robotic manipulation. He has a course on underactuated robotics that cover several of the topics that I described today. But to be able to really sort of implement from a holistic perspective, any of these systems, there's many more things that one has to go in depth into, right? So machine learning, definitely, right? So many of the students, if not all of the students in robotics today, they take machine learning courses. And today in particular, and for the kinds of systems that I described, that I showed today, some kind of sort of comfort with visual data processing in the form of neural networks is very important. So yeah, I don't know if that helps a little bit, but I'd be happy to talk more if you want to offline.
Absolutely. Thank you, Professor. This was a really cool talk.
The next question I'm going to ask, this is from Sayed. He first congratulates you on a nice presentation and very, very interesting work. And then he asks, how would novel actuators and soft robots or soft materials in general enhance the performance? So what is missing? Is it something where materials can change the game for your goals?
Yeah, that's a great question. Thanks. I think that soft robotics or soft materials is a double-edged sword, right? So on one hand, definitely, I think that it is not difficult to imagine many situations where they sort of facilitate interaction, right? So any situation where you need adaptability to shape, or you need to increase friction, or you need to what is the word? I forgot. Anyway, but yeah, so there's many situations where having some form of softness would make our life easier. On the other hand, for these to sort of for it to naturally blend into this kind of computational pipelines for generating behavior, we want the softness to be structured, or at least to be predictable. We want to understand when is a good idea to exploit softness and when it's not a good idea to exploit softness. And for that, you need a model that tells you how that softness is going to react or is going to behave. Compliance, for example, in actuators, that's fantastic, right? So if you have a robot arm that can implement impedance control, that's great. You understand how each one of the joints is going to react. If your end effector is sort of deformable in a way that is difficult to understand or is difficult to predict, eventually it will be difficult to integrate with dexterous manipulation pipelines.
That makes sense. There's one more question from George Chen, and George should be able to use his microphone.
Hi, Professor. Thank you for the talk. It was very interesting. Thank you for the talk. My question is, like, for the studies with the visual and the tactile sensors to manipulate boxes and bottles, if other people have like slightly different variants of these sensors, do they have to retrain the whole model over again, or how repeatable are these results from a study?
Yeah, that's again a fantastic question. So in the first project that I showed, where it was sort of using tactile feedback to guide reactive behavior, we didn't learn any models when it comes to processing the tactile data, the tactile feedback, right? So in that case, the processing was very modular, and we were extracting geometric features or sort of force features from the sensor, and everything else that comes after extracting those features is consistent throughout the system. So there would need to be some kind of calibration of the sensor to make sure that the way that you extract those features is consistent. But I would say that in that context, I don't expect too many issues in terms of transferability of the algorithms. I think it is in the case that some of these models are learned that we have a weaker understanding of how to make it sure that we can transfer those results or transfer those learned models. For example, we have another project in the lab that does that works on inserting objects for peg insertion with tactile feedback. And there we use sort of deep reinforcement learning to learn both at the same time feature extraction and insertion policies. And in a case like that, it is very difficult to sort of maintain the conditions under which the models don't degrade over time, even if it's the same sensor, because these processing pipelines have sufficient capability to be able to overfeed to any specific conditions of the experimental setup that you're running, even if they're not apparent or obvious.
Alberto, thank you. That is the end of the questions. And because it's already almost 5:15, I think this is a very good point to say thank you again. This was a fantastic presentation. And thank you to everybody who has been sticking around, listening to this excitedly, and also asking a lot of questions. Thank you. That terminates
Thank you,
our
Matthias.
pleasure.